In this video, we're going to look at the relationship between the volume of a gas and its temperature, and this is known as Charles's law. So let's just give this some thought. So if a temperature of a gas is increased, what will happen to the volume if all other conditions, and importantly pressure, remain constant? So pressure remains constant, which means that the particles have to hit the container the same number of times as before the temperature increase. So the temperature of gas is increased. Well, what's going to happen is the volume is also going to increase because the gas molecules have started moving faster. So they're going to have to take up more space in order for the pressure to remain the same. And you can look at that in the other way. If the temperature of a gas is decreased, what will happen to the volume? Well, the volume will also decrease because the gas molecules are now moving slower and will take up less space. So the relationship for volume and temperature is a direct relationship. When one increases, the other increases, or when one decreases, the other decreases. So this relationship between temperature and volume is known as Charles's law. And in words, Charles' law states that the volume of a given amount of gas is proportional to its temperature when the pressure is constant. And this can also be expressed mathematically with this equation. The initial volume over the initial temperature is equal to the final volume over the final temperature. And we can use that equation to calculate for one of those unknowns. So first, let's talk about the units that are needed when we're using Charles's law. So the volume can be in any units as long as the initial volume is the same unit as the final volume. However, the temperature must be in Kelvin in order for Charles's law to hold. So not degrees Celsius or Fahrenheit, but Kelvin, which is probably something you haven't heard about before. So what is Kelvin? So the Kelvin temperature scale was developed by Lord Kelvin in the mid-1800s. And the 0 point of the Kelvin scale is equivalent to negative 273 degrees Celsius. And this 0 point is considered the lowest possible temperature of anything in the universe. This is the temperature in which all particles cease to move at all. So this is called absolute zero. So absolute zero, which is 0 Kelvin, is equal to negative 273 degrees Celsius. So in order to convert between Celsius and Kelvin, if you have Celsius and you want to get to Kelvin, you add 273. If you have Kelvin and you want to get to Celsius, you have to subtract 273. And note that it's not degrees Kelvin like it is degrees Celsius, it's just Kelvin. So let's look at an example of using Charles's law. So using a glass syringe, a scientist draws exactly 25.5 cubic centimeters of dry oxygen at 20 degrees Celsius from a metal cylinder. She needs to heat the oxygen for an experiment, so she places it in an oven at 65 degrees Celsius and leaves it there for 30 minutes. Assuming the atmospheric pressure remains the same, what volume will the oxygen occupy? So let's list our givens. We have an initial temperature of 20 degrees Celsius. We have an initial volume of 25.5 cubic centimeters, a final temperature of 65 degrees Celsius, and we're asked to find the final volume. So the first thing we need to do is convert those temperatures to Kelvin. So we add 273 to each of them to get our initial temperature of 293 Kelvin and our final temperature of 338 Kelvin. So here's the equation for Charles's law. So we're going to substitute in the variables, the values that we know. So 25.5 centimeters cubed over 293 Kelvin equals a final volume over 338 Kelvin. So we need to isolate the final volume by multiplying both sides by 338 Kelvin. Kelvin cancels. So when we put this into the calculator, 338 times 25.5 divided by 293, we get a final volume of 29.4 centimeters cubed. So that's our final volume after the oxygen in the syringe has been heated up. You may also need to solve for an unknown temperature. So just a little review. If you need to rearrange to solve for temperature, you would start by cross multiplying. So you'd get that VI times TF equals VF times TI. And then you could then isolate the temperature by dividing by the volume, depending on which temperature you wanted to find. But this shows you what you would do if you were looking for the final temperature. So your final temperature is going to equal your final volume times your initial temperature divided by your initial volume.